All right, this is a video on incremental compounding related to growth of money in a bank account earning interest. And we'll start off with an introduction and then do a few solved examples. So first off, it's important to think about just what is compounding. When you deposit money in a bank account, you'll typically earn interest on that money. And the bank will add that interest into your account every period of time, maybe every year, maybe every month. But then subsequently down the road, you will be able to earn interest off of not just the principal you initially had in your bank account, but off of that new interest that has been added in. And this is what makes it an exponential growth scenario. You're not just earning future interest off of the initial amount you added to your bank account, you're earning future interest off of any past interest that has already been paid into your bank account. And that refers to compounding, and compounding can happen over different time periods. Compounding can happen over the course of a year, over the course of a month, every week. Compounding could happen, and we're going to look at that effect and look at a couple formulas we can use to determine how much money we'll have in a bank account in the future. So I have two formulas I'm showing here. The first one is just our standard exponential growth formula, where if we're starting with P, an initial amount, maybe a principal, P for principal, R for an interest rate, and T for time, okay? And I want to contrast that with this second formula where we are incorporating this variable n. N refers to the number of times compounding is happening per year. Okay, so let's write those. Let's have a little reminder of write those variables down. So P stands for principal or initial amount. R is your interest rate. It needs to be as a decimal. So if, say, you're earning 5% interest, you would enter R as 0.05. T is time in years. And N is the number of compounding periods per year. Okay, so those are a couple formulas to keep in mind. And make sure you're seeing that N shows up in two different spaces, two different places, shows up as the denominator of the fraction, and then in addition up in the exponent. So let's do an example with annual compounding, and then we'll look at an example with higher frequency compounding. So initially, let's say we have $1,000 we have in a bank account. We're earning 4.5% interest. I don't want you to think that that's a typical interest rate in a savings account in a typical bank, but just for the point of today's work, let's assume we're earning 4.5% interest. What will I have in 10 years? So we're assuming it's on annual compounding. Let's go ahead and run through our formula. So A I think can just stand for the amount we'll have after a certain period of time. We're starting with $1,000. We need to do 1 plus 0.045. And then we're raising that to the 10th power. Okay, so we're just assuming annual compounding at this point. You can type all this into your calculator. Even a basic scientific calculator should be able to do this pretty effectively and efficiently. I'll actually simplify a little bit first. My calculator advice is really to not have to write any intermediate numbers down, which would involve rounding and more writing than you need to do. Just type all this into your calculator and get an answer. And I think it probably makes sense for these financial problems to just round to the hundredths place, so we're rounding to the cents. So after 10 years, we'd have $1,552.97. Let's do a different sort of problem where we know our ending amount and we're wondering what our starting amount was prior to a certain amount of time going by. So maybe we have a goal of earning $10,000. We know we want to earn that over the course of 8 years. We know we have a 4.5% interest rate. How much do I need to start with? So if our formula that we're working with is this, we can simply solve for P, our principal, our starting amount, dividing both sides by this piece right here. And we will get our principal, or our starting amount, is going to equal this. and we can just plug in what we have. Okay, so here our ending amount, or A, is $10,000. Again, we're earning we're earning 4.5% interest, which turns our change factor, or our growth factor, the base of our exponential function, into 1.045, and our exponent is 8 for 8 years. Okay, so once again, what I would suggest you do is try to type all this into your calculator in one set of steps, and without having to write anything down, and then round to the cents place. So I get about $7,000, $7,031.85 as my solution to this one. We'll do a couple more problems here. This next one we'll do is, let's start exploring what more frequent compounding would look like. So we're going to repeat the first example we did, only with monthly compounding instead of annual compounding. And in the process, what I'll try to do is explain what some of the pieces of the formula actually mean, where they came from. So here we have our starting amount of $1,000. I think that's right. Is that right? Yep, $1,000. We're earning 4.5% interest. But what that really means is every month we are earning 1/12 of that. And so that's why we're doing 0.045 divided by 12. So what's the effective interest rate we're earning on a monthly basis? In other words, how much money, that'll inform how much money we need to add into our bank account as interest each month, or how much the bank will add in. And then how many compounding periods overall happen? 12 per year over the course of 10 years. That's why we do 12 times 10, to think about how many times we're incorporating this new interest, this newly earned interest, into our bank account. A very common mistake is to type all this into your calculator and then just left to right, and then you'll have a mistake right in that exponent if you don't either group the 12 times 10 in parentheses, or just multiply it ahead of time to get a 120, okay? You'll have an order of operations mistake. So that's something you want to keep in mind. Otherwise, any scientific calculator should be able to just handle this just fine. So I'm going to simplify this a little bit. And I'm going to type that into my calculator. And I get a final answer of $1,566.99. Okay, let's contrast that with what we earned in the initial problem. You can see we earned $1,552. So just the fact that compounding was happening more frequently, interest was added in more frequently, and we were able to earn interest off that interest more frequently, we were able to make about another $15 or so. And then the last problem we'll do today is thinking about which would be a better deal, a 9% annually compounding interest rate, or an 8.7% monthly compounded interest rate. Okay. Hopefully you can see that the more frequent the compounding, the more money we will earn, all of the things being equal. But in this case, we have a slightly lower interest rate with that lower compounding. So let's make things simple. Let's say we're doing this for a year, and let's say we're investing $1. So for 9%, we can invest $1 and raise to the 1 year. Okay. For 8.7% monthly, again, we're going to invest $1. That's that initial one. And we're going to take that 8.7% and divide it by 12, because that's the effective monthly interest rate. And we're going to compound that 12 times in 1 year. Let's see what we get. Hopefully you can see on the left-hand side, we just simply get a 1.09. So if we invest $1, we'll have $1.09 at the end of the year. We have a little bit of math to do on the right-hand side. And once I do that math, I get 1.9055. And I suppose if you were just rounding to the cents, it would be exactly 1.09. But hopefully you can see that the monthly compounding would give us a slightly higher effective effective interest rate, just because we're compounding more frequently, even though we have a lower interest rate overall. And that is a great place to stop right there.